I am really excited to have this panel here with me, and I'll have them introduce themselves. Let's just go down the line. Hanhee, why don't you introduce yourself and share a little bit about how you come to the topic.
Okay, so my name is Hanhee Paik. I'm a senior research scientist, and then also start doing the ecosystem development, especially in France, from IBM Quantum. And again, I have a PhD in quantum computing and also being exposed to the business. I mean, this topic is extremely important, especially from the point of view of the future of a computing architecture. So I guess that's why I'm here. Yeah.
Hi there, Sebastian Hassinger with Amazon Web Services. Is this one? Okay, there we go. I have a business development role globally with AWS in the quantum team. So that includes the bracket service, our R&D and qubits and networking, and our professional services offering as well. At Amazon, quantum is really, from a go-to-market perspective, is considered a subset of HPC. So we're really embedded in the HPC team, and we collaborate a lot with the HPC services that exist, parallel clusters and the rest of them. So.
Eppe, I'm in charge of the portfolio for HPC and quantum, developing it for EVIDEN, an Atos business. And basically we are, I am what we would say a veteran in HPC. And we are working for years on making HPC a big player in Europe for us. And quantum is just another angle to solving the problems. We are really looking at working on hybrid computing using AI and quantum as accelerators to HPC.
Hello everyone, my name is Jan Goetz. I'm CEO and one of the co-founders of IQM. My background, so I started on the academic side. I have a physics background, and at some point together with my three co-founders we decided to spin out a company from Aalto University and the VTT Research Center in Finland, which is IQM, and we have meanwhile grown to, let's say, the largest effort from Europe in building quantum computers based on the superconducting approach. So we have around 250 employees, and our focus is actually very much bringing these quantum computers into the HPC supercomputing centers and combining them. So I'm very much looking forward to the discussion today.
Terrific. Well, thanks for that. As you can see, we've got an esteemed panel. And let me start the questions. One for you, Hanhee, actually. So everyone else has talked about the complementarity of HPC and quantum rather than kind of competing for workloads. How does IBM see it? Are you of like mind? I mean,
I think IBM, we are seeing the whole thing as more like a, for a computing perspective. Yeah. So it's not like quantum computing, it's not like classical computing. I think both can be very useful for, the bringing the computing services to the users. And again, our vision in the next many years is the bringing this quantum-centric supercomputer, where the quantum computer is integrated together with any classical computing like CPU, GPU. We have integrated workflows such that any algorithms, either utilizing classical algorithms and a little bit of the quantum embedded, or even quantum algorithms that a little bit of the classical embedded, can be run in that computing, quantum-centric supercomputing systems to bring the useful results to the users. I think that's the whole vision. We are definitely working towards that way. I think we have a roadmap that already explains up to 100,000 qubits beyond 2026. And we are working with a lot of supply chain enabling technology companies to bring the necessary components towards that. And and again, our future is like a modular architecture that's connected through the quantum communication links. And we are going to build also the middleware so that the whole system can run seamlessly. So that's the sort of the high-level view of the technical view from IBM. Yep.
Terrific. And this one really is for the field, but it's probably worth starting. Eventually we're going to get to the challenges because this is a quantum computing panel after all. But I'm really interested in hearing a bit about the vision for integrated HPC quantum computing, and what the benefits are. And it's really for the field, so whoever wants to start, but anyone feel free to weigh in.
Yeah, I'll jump in. So, I mean, At this stage, we've built hybrid jobs as a feature on Bracket, where you can attach an arbitrary container a container of arbitrary code, classical code, and run variational type jobs. But it's really much more open-ended than that. It's sort of an integration point, an extensible point to add classical compute horsepower to a quantum job in any way you want. So it could be machine learning or other simulations and other use cases. So that's kind of the stage we're at right now. I think we see that developing over time to a combination of either combination of larger scale classical compute resources in the cloud along with cloud-based quantum, or on-prem, of one or either or both. Eventually we see systems like IQM, for example, in an HPC center along with an on-prem cluster. And the need then will be sort of orchestration of all of these moving parts in the cloud and on-prem in a seamless way.
Maybe to add, so of course these, let's say, variational cases and use cases, this is kind of very obvious on the application side. I think something one should also always consider, and this very much depends on the implementation in the end, but it's the error-corrected systems, where actually, at least in many implementations, you will need a very strong backbone of a HPC computer to implement the error correction. So I think also if you look at certain visions for error correction, I think the hybrid approach has a very important role to play.
That's really interesting. So beyond just the variational, which is like necessarily partitioned, you're saying even for a error correction scheme, having that integration, it has advantages. Interesting. Yeah, go for it.
Eric didn't speak, so this is first, and then
No, I think you said it, but I think the important thing for us is that what is the scope? What is the time frame for that? Because we are speaking about, IBM is speaking about large scale quantum, which we know will take some time to get there, and we think that there is a way to do things before large scale, right? So there are some implementations that can happen before that, and then we start seeing some customers with applications willing to benefit from quantum computing and start seeing some scaling factor in the applications today, right? With existing hardware, with existing simulation environment, and if they combine correctly the supercomputers of today, plus some AI mechanisms, plus some quantum hardware or quantum software, they can benefit from quantum now. So, and then in the future, when large scale is happening, and we don't know when still, we will combine, everyone will combine all this technology. I think the vision that everything will be quantum, the general quantum computer is going to be very far from now. Maybe this is at least my vision. So what do we do between now and then is really the question. And hybrid computing is really the answer, I think.
Can I add a quick?
You can, but I insist that you also, if you have a difference of opinion, also debate Eric on the timeline.
No, because because computing is a computing, right? I think the question is how we can use the existing computing for usefulness that we can use right away, and I do think that we definitely use something. Especially now, a lot of researchers are working on how we can utilize both, or quantum and classical. There are a lot of techniques, error mitigation technique may not need HPC, full HPC, but that's one of the examples that a lot of classical processing is required, and the result definitely helps to improve the quantum computing results. They are a circuit needing algorithms that actually requires a HPC level of the computation, because we are trying to simulate or emulate these entanglements using classical, but we cut off the circuits so that a lot of parts can be run in quantum computing. So that's another area that people are looking into. And dynamic circuits is another thing. That's the quantum operations that utilizes the measurement feed forward to the circuits, and that actually can reduce the number of quantum operations and that's very helpful for running actually useful applications. So those things are actually those things you can utilize and or take advantage of the classical computing that's integrated with the quantum computing. And I'm hoping that maybe scientists can develop more algorithms like that to reduce the computation resources and make the existing one useful.
So we're talking about applications, and this is still in the benefits stage of the discussion. I had noted at the top of the discussion that there are really two fast-growing segments in HPC. One is exascale computing, which is a small market now, about $1 billion, but growing very fast. And the use cases there tend to be scientific use cases. Actually, a lot of the things that in small scale that quantum computers will hopefully be able to do at a large scale. The other one is the cloud segment, and the use cases there are almost entirely different. They're largely AI driven use cases. Sometimes things like foundation model training, et cetera. And this one, I'll start with Jan. But in your view, for applications of quantum computing and HPC, is it more likely an accelerator on that exascale portion of the HPC, or do you see it being equivalently applicable to AI and the kind of cloud-based use cases? What use cases do you see as benefiting most from an integrated vision of HPC and quantum?
Well, I think at least in the, let's say, mid-term, I'm thinking of it more like an accelerator kind of things, really working hand in hand together. And I think then if we talk about these more long-term visions, I think it really depends a lot still on the algorithm development, what is going to come there. But our thinking is really to use them as an accelerator, and this is why we are bringing the quantum computers into these HPC centers. And in our case, this is still mainly scientific computing centers, where the question really is, let's say, fundamental quantum physics, such kind of simulation. So this is what people are interested in. And of course, this is still very early days. So we are still discussing how should it be done, what is the best way to connect the systems on the software level, maybe even on the hardware level, all of these questions.
Yeah, I think if you look what's happening in Europe, at least the market I know well, is we are working now on the future exascale procurements. And mainly what it says is we will have probably two big exascale systems in Europe. One is for sure in Germany at Jülich, and the other one is not known yet, but there will be a big one. But both of these sites have been awarded, I would say, in some European program to enable quantum computing with large-scale HPC. There's some Euro HPC programs working on that, and so they have funding for that. They have acquired some quantum computers, and today, together with IQM, for instance, we are working on some ways to implement hybrid computing for that purpose. So, right, so it's an ongoing thing. I agree with Jan. It's more scientific exercise to make sure that we find a way to really hybridize the two systems together. And one of the topic that is really important is variational algorithms that we need to make work. And all the machinery that needs to happen in the end.
Yeah, I would say in some ways you can see this as a challenge for the scientific applications. You were talking the exascale is very often public sector funded and a scientific research resource. If you look at the other side of that, the machine learning and AI, that's been primarily driven from the private sector. And I think in some ways the challenge is for these HPC centers to adapt the learning from AI and ML. You can think about data science and big data sort of evolving into the current state of AI and ML. And a lot of what happened was sort of streamlining of the tool chain for access to resources and deployment of models and code from prototyping in notebooks to actually deploying into a production environment. I think a lot of that can be valuable when adapted to the scientific regime or scientific simulation regime. In dealing with the complexity and heterogeneity of classical and quantum and cloud and on-prem altogether. So that's sort of the direction we see.
I mean, I wonder also, if traditional problems that you use exascale probably can be still applied to these quantum plus exascale systems, right? And I think someone mentioned the embedding. I mean, that's another example that, you solve the chemistry, the larger molecules or, chemistry systems. I think that'll be probably one of the big or good applications that you can try, especially like you do the mean field calculations in the HPC or exascale system, and then you just do the, more active part of the molecules to use a quantum computer to solve and things like that, yeah. So, yeah.
So in US constitutional law, the Fifth Amendment allows you to, or gives you the right to not incriminate yourself. So when we say you're allowed to plead the Fifth, it means that you don't have to necessarily answer the question. Sebastian, for you, I have a question for you, which I give you the right to plead the Fifth. Do you think that it's inevitable that all major cloud computing providers will build their own quantum computers?
Inevitable. That's a really good question. I mean, we see this as a landscape that we don't expect to sort of converge on a single platform. And you look at classical compute on AWS. We've got Intel, AMD, NVIDIA. We've got FPGAs. We have our own chips, and it's a customer's choice. So the workload dictates, and the enterprise requirements dictate the choice. I think that we expect the same thing in quantum. We don't really see our efforts to build our own qubits as competitive so much as collaborative. It makes us understand, have skin in the game and understand our QPU vendor partners and how hard it is to build these things in a way that we wouldn't understand if we weren't doing it alongside them. Right. So I see it as being much more of a collaborative endeavor for at least the foreseeable future.
Yeah. That's what I would have expected, just based on the fact that even though there's an enormous market sizing, of course we've done the market sizing, for quantum workloads in the future, in terms of overall dollar value for hyperscalers, it's actually not actually that massive. Right. So you could imagine procurement still being an option. All right, well, let's transition now to some of the challenges of the integration. And I don't know, Eric, do you want to start maybe with what makes it difficult to do the very integrations that we're hoping will provide the benefits we've just described?
Where should I start from? So it goes all from. So I think it's mostly about software, right? So we have QPUs on one side, I mean hardware on one side, we have supercomputer on the other side, we have other types of environments, and we'll see other environments, as you said, there are FPGAs, maybe they will offer some solutions. We have AI in some, I think when I say hybrid, I mean it must be, and it will be, I think, a collections of different technology that will mix together to accelerate the workloads, right? So the thing that we understand is when we are talking supercomputers, we are talking gigahertz, right? Mm-hmm. When we're talking QPUs, we're talking hertz, right? Roughly.
Kilohertz.
Maybe.
Kilohertz, maybe. Okay. Okay, so there's a scale. Yeah. And this is a difficulty because when you say variable algorithm, for instance, okay, you have to instantiate your circuit to the QPU and then change a parameter, and you have to do it as fast as possible, but it's not the scale of a supercomputer. Yeah. And so basically we're trying to accelerate where you have a device that is much slower than a supercomputer. Yeah. And so there will be some, so you need to find a way to make it the more efficient possible. Don't lose the time of this very, 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 very specific, very expensive device. And so it's very difficult today. So it will evolve. We will find ways to make it happen. But it's difficult because you have this thing, this object that is very expensive. I always take the image of you have this Concorde, if I will, yeah. Concorde plane, right? Very expensive. Only 100 seats, right? But behind you have millions of people willing to use it. Okay, so what do? So you either queue to get a seat on the Concorde, or you use another way to do it. So, for instance, simulations, other, I would say, faster device but cheaper devices. So we need to find a way to make it accessible.
Yeah.
But remember, at the beginning of IBM, when they started, the biggest computers, they were only for NASA, right? Only a few people had access to them. It's the same thing today. If you want to use one of them, it's very expensive, only a few people can access, and it's hard to access. So how do you do that? Is, I think, software at different levels, and probably, I think, this is why we are still willing to do some simulation environment, because simulation has a big play here, I think, because it would be not the Concorde, but maybe the 747.
Airbus is right there, 380, right?
380, yeah.
But I really like the points there about obviously there's speed and costs and accessibility. I don't know, Hanhee, anything that you would add in terms of barriers? I mean, I know that you guys are, IBM is particularly advanced in terms of bringing the two together in a near term, right? So in the long term, some of the things around speed may go away, right? If you had a full-scale, fault-tolerant quantum computer. But I don't know, any other near-term challenges that you've seen in your practical efforts to bring them together?
Yes, I mean, the time scale is, I guess Eric mentioned just there. I mean, time scale for different steps of the workflow, that's a challenge. That's actually like more practical, something that we have to solve, right? Sure. So how to interface that, or how even to design the workflow. We don't even know the computing architecture. Actually, we know, but it's not known. Or there's something that people have to research, that what would be the most efficient, the workflow architecture design that we need to do to be more flexible, how to make it more integrable with the different computing. And I mean, also, personally, I think that developing the algorithms that make the best use out of this architecture is also the big topic of the research.
Yeah. That seems quite consistent, Eric, with your perspective. Yeah, Jan.
Maybe, just to add, because something that's, I think, in the very beginning, often the hurdle is actually the communication and the language that people speak. So I come from the quantum side, and maybe I have an idea on how to talk about entanglement. But on the supercomputing side, people talk about petaflops, right? Yeah. So how do you connect entanglement with petaflops? And it's not easy, right? How do you compare, and how do you somehow bring the different people to the table and make sure that they speak the same language, learn speaking the same language, and understand, okay, this is actually what they're trying to tell me, and this is how it translates into my problem. And I think this is something we all need to work on together from the different sides that we are coming to. And I think that's very important, because if people don't understand each other, they also don't understand the value that is being created. So this is one thing. And then one very obvious thing, because you talked about software, of course also on the hardware. So people ask me, why does it even make sense now already to bring systems into these centers? But these are very trivial questions, like what are the specs for the cooling water? How big is the door? Does it even fit through, right? So such things need to be figured out if we, once the industry scales, if we want to be able to actually do it. So I think there are many layers still that need to be solved, and I think for all of those, it's better to start early, already now, if we want to have the right capabilities in the future once the industry is really adopting the technology.
And just to amplify what Eric was saying, just comparing to the earliest days of classical computing, in a sense, these quantum systems are like pre-microprocessor, vacuum tube or electronic-based computers. They're being driven by scientific computing, right? The Manhattan Project and other scientific applications were the initial drivers, the development of those machines, and then they were slowly commercialized through development of other algorithms like Monte Carlo, et cetera. And the difference being that we also have hyperscaler clouds and petaflop exascale computers and open source software and very sophisticated tooling. So it's almost like, what would you do if you were in 1952 developing the first large-scale computers, but you also had the cloud and open source software to help you?
Yeah, it is. It is sort of an unprecedented challenge in some ways, and then there's parallels in others to early days of compute. So I wanted to, I'm going to ask one very anodyne technical question, and then I'm going to ask a slightly more provocative question in that order. So the first one, Jan, you were talking about like the different languages of of HPC in quantum, and I think that you certainly got a big thumbs up from Hanhee, which you may not have seen. One thing that they have in common is that interconnects are a really big problem, even in HPC, right? It's a big blocker, and there are attempts to actually use photonics there as well. Is there any, I don't know, continuous technology development that actually, could the interconnect problem be a bridging point?
Well,
anyone, yeah.
I mean, the superconducting processors that we are using, they're working in the microwave regime. But this doesn't mean that you cannot use photonics at all. So if you think about these systems, and often you see these golden chandelier-like structures, and you see all these cables going down, because we bring the microwave signals from the top to the bottom. But actually what you can do is you can bring the signals in the photonic regime down there, and then you have a converter. And in this way, actually, you could use the photonic interconnects, and that then only on the processor level you convert to microwave regime and use the signals. And this, many people are working on this, both on the academic research side, but also there are several companies who are working on it. And I think this will be the kind of future for really scalable systems. And I think this might be then a way to combine all of those technologies.
So the transducer, so converting microwave to optical and optical to microwave, that's still like in the area of the research. So as far as I know, I stopped reading papers until like last year, but then I don't think we have a high fidelity single photon conversion, which is required to deliver the quantum information. No one demonstrated that yet.
Yeah.
But this is an excellent topic here, because in France, there are a lot of people working on, the quantum communications and, quantum transduction. So I'm hoping that any of you guys could probably solve the problem. But definitely the optical interconnect can give us more flexibility to connect the different systems modular, because that's a room temperature connection. So as long as you have the transducer developed, then, you can disconnect and connect. Because another way will be cool, like cryogenic microwave links. But that's much less flexible, because you have to kind of integrate it within the cryogenics, right?
Yeah.
That technology is more developed. You can have a high fidelity single photon, connections through the microwaves. But I think that's the direction that we are aiming for. At IBM, we are aiming for in the next few years. But I think that it'll be great to have this optical interconnect. Yeah.
And ion traps as well, need that bridging from one trap to another through photonics. So similar challenges there for scaling.
And then it's not even easier for them either, because they still have to convert to the telecommunication frequency, which is not the frequency they're using for computing.
Well, you guys are getting into my next the more provocative question, which is to say, are there certain physical implementations of quantum computing that lend themselves better to an integration with HPC than others? Like, in other words, is it easier if you have a superconducting machine to integrate with HPC, or an ion trap machine, or cold atoms?
Maybe just a hint on that. I think with today's packaging of a supercomputer, an ideal platform would be the one that needs no cooling, or no big cooling, I would say. No cryogenic cooling. And let's say silicon that you could, or silicon or optics or whatever that you could just integrate into a rack would be better, because this is what we know and we do well, and the industry. Sure. Because this is one of the big challenges, right? Today, with today's supercomputer, cooling is really one of the biggest challenge. It's getting hotter and hotter. We don't need to be, at the two sides of the same coin, where you have to cool something which is 100 degree or close to 100 degree, and something which is 0.05 Kelvin or whatever, at the extreme opposite. And so it's really something that is a big problem. Today the two things are separated, and they are not in the same room, and we cannot integrate them together. But if we had a silicon that could be fitted into our racks, it would be good.
But I think probably from the beginning will be quantum computer is connected to the HPC room temperature. And probably the information that they should exchange will be classical information. So probably the measurements from the quantum computer is processed in the HPC. Probably that'll be like what we are going to see in the next 5 years, potentially. But again, at there, we still have the problem, not problem, but like time scale difference, right?
Yeah.
Because classical information from, or measurement outcome from quantum computing is coming at kilohertz or megahertz. And, or actually, I'm only talking about superconducting qubits, but, And then HPC, they can process those information way faster than, the quantum. So I think either like architecture, like maybe multiple quantum computers connected to one HPC machine in parallel, and then maybe there's a software in classical computing that processes the outcome of the quantum computing, and then they can probably like combine those results together. Some parallelization software in HPC that processes the quantum outcome or quantum measurement outcome. I think those things are the ones that probably we have to work on it right away in the next few years, to make it more useful.
Yeah, and I'll dodge the controversy by saying that is the billion-dollar question, right? It's a race to quantum advantage versus ease of integration with the HPC center, right? I mean, obviously, silicon-based or photonic-based would be fantastic. Superconducting, trapped ions, neutral atoms to be closer to realizing some kind of near-term advantage. And that's the nature of the horse race. And legitimately, that's the sort of motivation behind AWS investing in Bracket as a multi-device service. It's, don't put all your chips in one. As a customer, don't put all your chips in one slot. So
maybe to bound on what you just said about silicon photonics and interconnectors, interconnections between supercomputers and quantum computers. I think one other topic that is very important that we don't know how to deal today is how much data we can bring to these devices. Because today it's not data friendly. You cannot load a lot of data to this, and this is a big difference between supercomputers because supercomputers are massively driven by data, including mostly AI. But if you don't have data in HPC, traditional HPC, it won't work, right? So, and Exascale is willing to get more and more data. So I have no answer today. I get no answer from the industry. How much data can we will be able to feed to these devices? I think is a big question.
Yeah. Yep.
I don't know if Jan or Hanhee, you can answer that, but.
I think the challenge is that we call it a quantum computer, but usually in a computer you have a processor and a memory, right? Yeah. You have a different architecture because the quantum computers, they are just processors. It's more like an FPGA kind of in the way it works. It just processes data in real time, so to say. And I think, of course, there are ideas how to implement quantum memories, but similar to these photonic transducers, this is still very early stage and in the research phase.
But you agree that this is
I agree,
issue?
Yes.
So there's the data throughput, there's the timescales, there's cooling, there are all sorts of challenges. And I think, Sebastian, you kind of articulated very well the tension that I was hoping to tease out a little bit, where you have some platforms that are very far ahead, quantum platforms on an engineering, from an engineering perspective, and then others that may be more easily integrated with HPC, right? So, and that's of course, that's how it all worked out. So I think a lot to do. I think I'm really interested in folks giving a little bit of a future-looking view. Like, when would we see in a traditional data center? When would we see the integration of quantum? Like, what do we think is a realistic timescale for this to happen?
Are we not doing this year or next year?
Well, I was hoping you were going to say by dinner. Yeah.
Yeah. I see. I believe the prototype will be this. Coming in the next few years for sure. And we are working on it.
Yeah.
And I've talked to Eric before, also. And even
So
IQM also.
What we are doing together with Eric's team in Munich is happening now. So you can see pictures where we bring the system into the big cube, into the data center. So this is happening now. Of course, these are the first baby steps, and it doesn't mean that we have solved all the problems. But it is happening now, and of course we have a kind of a roadmap also on how to do this, and it's strongly supported by the European Commission and other programs who say, okay, we have these kind of roadmaps, the first processor now, and then we kind of increase the processors side, and it's all going to happen in the data center. So I think this project is a prime example that we are doing there together.
Yeah, and if you look at the big sites in Europe, like Jülich, I just mentioned this one, but LRZ is another one. Jülich, they built a specific building for that. They will host two quantum computers there. GNC in France is going to have one hosted at the TGCC close to here. So I think it's happening now. It's in the process today.
Yeah, and I think that's it is initially sort of with IBM selling systems to Fraunhofer and University of Tokyo. That was sort of initial steps, and I think there's a lot of value in even at this stage before there's a quantum advantage in sort of working out the operational type of integration and having a way to build up the institutional skill around the care and feeding of these devices and the integration and operation.
Do you see this, and this may be mostly for Erica and Sebastian, do you see this as largely an on-prem kind of in the near term?
No.
No? Okay.
I mean, AWS, I have to say no.
Yeah.
I think it's going to be a hybrid approach. I mean, I think, HPC centers aren't exactly going to go away because there are use cases where having a large on-prem resource makes sense.
Yep.
Where the cloud excels is flexibility, right? So
Yeah.
if you've got a huge cluster that's in high demand from your research community and you want to prototype your approach on something quickly, or you have the ability to burst out to the cloud is incredibly powerful, right?
Yeah.
And we can do large-scale stuff in the cloud that does fit some sets of requirements, and I think the same will continue through quantum as well. There will be some use cases where having the hardware physically co-located and having InfiniBand between the two, or whatever the fastest way you can integrate them makes sense, and in other cases the cloud will be perfectly adequate for and excel in those other use cases.
So I think that you should differentiate the consume, how you consume the other thing, right? So the big centers, the HPC centers, they will want to get a QPU on their prem. Then how do they consume it? Could be directly connected to the supercomputer, or maybe, and we are working on that, offering a platform to consume it as a service on a platform. And this is two things. On the other side, and so these centers have the money to buy these expensive devices. But I do see in the future, and I agree that some of the consumption will be made through CSPs, but on the other hand, think of financial institutions. I believe that none of them, or a very small portion of them, will use CSPs to do that because they don't want their data to be uploaded somewhere, right? So they will buy QPUs. They will put them on their prem. Maybe there will be some hosted with AWS or with any CSP, but I believe there's you should differentiate the where it's located and the consumption model. Yeah. And the consumption model will be mostly, I think, as a service, but could be on-prem as a service, like a private cloud.
And it's hard to see where that, because there's still a lot of movement to the cloud, it's hard to see sort of where the water level will rest with that. But ultimately, your point is, it should actually mirror the classical workloads, which remain on-prem, understand, for select use cases. Okay, I've got one last question, which I feel compelled to ask because we are in France, where environmental concerns are always sort of top of mind, and because of the well-known and kind of recently well-publicized costs of computation, specifically around foundation or generative models in the cloud and training. Do we think that quantum computing has the potential to be to the benefit of data center energy footprints over the next, I don't know, in a medium term and in a long term?
I mean, absolutely, right? Once we have a quantum advantage, then it'll definitely place that power of the computation with the quantum. And as far as I know, I think quantum computing still consumes much less energy than the classical computing. Because I heard about this, ChatGPT, that they are consuming tons of GPUs, and that burns like a lot of energies, right? Like if you go to the data centers, like I've been to RIKEN before, like in Japan, they're like a water burning every day, and that's all energy just evaporated to the air. So I think quantum computing definitely is also a good alternative in the computation in terms of a sustainability, for sure. Yeah, I think.
Just at the point on what you just said, I heard 2 weeks ago that the consumption for ChatGPT 4, 450 megawatts. 450 megawatts. So we are talking for an exascale system, maximum of 20 megawatts. So just the scale is just a big stretch. So I think from what I hear today, from a superconducting device, the consumption is much less, right? So there will be a dramatic improvement, I guess. But yes, I hope so, at least.
Yeah, absolutely. I mean, I think there is definitely hope in the longer term. In the near term, as a shameless plug, there are ways that we can optimize our power consumption even today. So in terms of model training, our ARM-based Trainium and Inferentia chipsets are something like 65% more efficient for training and running models. So there's a lot we can do in the near term. We don't have to wait for quantum to sort of save ourselves.
Of course.
Maybe just one additional thought, because speaking as a physicist, energy is power multiplied by time. And now we've been talking about the power consumptions, megawatts and whatsoever, but also the promise of quantum computing is that you can solve problems that would take whatever years or hundreds or thousands of years in more human timescales, right? And this is another factor one has to calculate in, that it's not only the power consumption, but it's also how long do you actually consume this power if you want to solve a problem.
Energy and time, yes. Both.
Yeah.
Terrific. Well, thanks so much for your very thoughtful answers. And thanks to the audience. This has been a great conversation.